Hello, everyone, and a very warm welcome. Today, we're going to dive into a really fascinating topic, Markov networks. Now, I know many of you are already familiar with Bayesian networks, right? Where everything is about cause and effect, sort of like a strict hierarchy. But what happens when the relationships are more like partners or friends working on a project together, where the influence flows in both directions? How do we model that? Well, that's exactly what we're going to find out.
So let's start with a little puzzle. Think about it. In a group of friends or even in a family, influence isn't always a one-way street, is it? It kind of flows all over the place, all at once. So the big question we have to ask ourselves is, how do we represent this kind of mutual back and forth relationship in a mathematical model? This is precisely the challenge we are going to solve today.
And to understand this properly, let's take a simple, relatable example. Meet our 4 students, Anjali, Brajesh, Charan, and Divya. We'll just call them A, B, C, and D to keep things simple. They're all studying for a big exam, and the way they study together is, well, it's very specific.
Okay, now let's lay down the rules for our little study group. It's a simple circle. You see, Anjali studies with Brajesh, Brajesh with Charan, Charan with Divya, and Divya studies with Anjali, closing the loop. But please, you must pay very close attention to these last 2 rules. They are the most important part of our whole problem. It's this. Anjali and Charan, they never study together. And in the same way, Brajesh and Divya, they never study together. Got it? Remember that.
So our goal is to build a graph, a model that perfectly captures all these connections, and just as importantly, those disconnections. So the first tool we'd probably reach for, our usual suspect, is the good old Bayesian network, with its directed arrows showing cause and effect. Let's see how it handles this. All right, let's look at our first attempt here. We have arrows pointing from A to D and B, and then from both D and B into C. Now, this model, it gets one thing right. It shows that Anjali and Charan aren't directly connected. That's good. But, it creates a very big problem. Look here at node C. When 2 arrows point into the same node like this, we call it a V structure. And in Bayesian networks, this means something special. It implies that if we know what C is doing, it suddenly creates a dependency between B and D. But our rules said they never interact. So this model is wrong. It has failed.
Okay. Attempt number 2. Let's try shuffling the arrows around. Here, we have arrows going from D to C and A, and from B to C and A. Again, it correctly shows that A and C never study together. But now it makes a totally different mistake. It implies that B and D are completely independent of each other, always. But we know that's not quite right. Their study habits are linked through the others. The truth is, no matter how we arrange these arrows, we simply cannot find a Bayesian network that can perfectly map our little problem.
And this brings us to the heart of the matter. The problem isn't our arrangement of the arrows. The problem is the arrows themselves. You see, a directed edge from A to B implies that A influences B, a one-way street. But in our example, Anjali and Brajesh are equal partners. The influence is mutual, it's symmetric. A directed graph, by its very nature, it's just the wrong tool for this kind of job. It simply cannot capture this type of relationship. So, if arrows are the problem, what's the solution? Well, it's actually quite simple. We just get rid of them. This is where we move away from directed graphical models and introduce our hero for today, the undirected graphical model, also known as the Markov network.
And just look at this. So simple, so elegant. We just connect the students who study together with a simple line. A is connected to B and D, B to A and C, C to B and D to C and A. This captures everything perfectly. It clearly shows A and C are not directly connected, and B and D are not directly connected. Yet it shows they're all part of the same connected system. This is the perfect map we were searching for.
So this is great. The structure makes sense. But this brings up a very, very important question. If you remember, in Bayesian networks, the arrows gave us parents and children, which led us very nicely to conditional probability tables. But here, there are no parents. There are no children. So how on earth do we assign numbers to this thing? How do we measure the strength of these connections? The answer lies in a brand new concept. Instead of probabilities, we're going to use something called factors, or sometimes potential functions. Now, I want you to think of a factor as just a simple scoring system. It's a small table that gives a score to every possible combination of the connected variables. This score just tells us how compatible or how much affinity those variables have for each other. Now I'm going to repeat this because it is very, very important. This score is not a probability. It is just a number that represents compatibility. Take a look at these tables here. These are our factors. For the pair Anjali and Brijesh, when they're on the same page, let's say A equals 0 and B equals 0, they get a high affinity score of 30. They're very compatible. But if they disagree, say A equals 0 and B equals 1, the score is much lower, only 5. Think of it like food, okay? Paneer tikka and naan? Oh, high compatibility score, a perfect match. But what about, I don't know, idli and butter chicken? Not so much, right? A very low compatibility score? That's all these factors are doing. So we have all these compatibility scores, but what we really want in the end are probabilities. So how do we get from one to the other? It's a simple 6-step process. Just follow along with me. 1. You pick one possible state for the whole system. For example, everyone has the value 0. 2. For that state, you go to each factor table and look up the matching score. 3. You multiply all those scores together. This gives you one big number. 4. You do this again and again for every single possible combination of states. 5. You add up all of those big numbers to get one giant total, which we'll call z. And finally, step 6. You take each individual big number and divide it by that total, z. This last step, which we call normalization, is what magically turns our simple scores into real probabilities.
Now, to make this crystal clear, let's just walk through one calculation together. Let's take the very first case, where all our students, A, B, C, and D, all have the value 0. We go to our factor tables. For the first factor, between A and B, the score is 30. For the second one, between B and C, it's 100. For the third, C and D, the score is 1. And for the last one, D and A, it's 100. Now, we simply multiply them. 30 times 100 times 1 times 100, which gives us 300,000. It's as simple as that.
And then we just repeat that exact same process for every single row you see in this table. For each combination, we multiply the factors and get an unnormalized value. Now, if you take that entire unnormalized column and just add up all the numbers, that grand total is our magic number, z. This total, z, has a very special name. It is called the partition function. You can think of it as the great normalizer. Its only job in life is to be the denominator in our final calculation. When we divide each of our individual unnormalized values by this one big number, z, we guarantee that all our final numbers will behave like proper probabilities. That is, they will all be positive and they will all add up to 1. It's the number that makes all the math work out perfectly. So we have seen how to build and calculate a Markov network for our simple 4-student example. But what is the general rule? What is the deep principle that's really going on here? The answer lies in the power of something called cliques. Let's look at a slightly more complex graph for a moment. What is a clique? Well, a clique is simply a group of nodes in a graph where every single node is connected to every other node in that group. Think of it as a super tight study group, a little circle where everyone knows everyone else. In this example here, the nodes A, D, and E form a clique because A is connected to D, D is connected to E, and E is connected back to A. They form a little fully connected triangle. And this brings us to the most important theoretical idea of this whole session. The fundamental difference between these two types of models is how they are broken down or factorized. A Bayesian network, as we know, is a product of probabilities defined over each node and its parents. But a Markov network, it is a product of these potential functions, these factors, defined over the maximal cliques of the graph. Maximal just means the largest possible fully connected groups you can find. So one model is built on parent-child links and the other is built on these tight-knit groups. So we have gone on a journey today, from a simple puzzle about 4 students to a powerful new way of seeing the world. We've learned that when there's no clear cause and effect, but instead a network of mutual influence, Markov networks are the perfect tool. So I will leave you with a final thought to ponder. Now that you understand this pattern of mutual influence, where else do you see it? In your circle of friends? In the pixels that make up a digital image? Maybe even in the stock market? These undirected relationships, they are everywhere once you know how to look for them.